Reheat cracking damage mechanisms is a part of mechanical and metallurgical failure mechanisms. Description: Reheat cracking damage mechanisms based on API 571, cracking of a metal due to stress relaxation during post-weld heat treatment, or PWHT, or in service at elevated temperatures above 750 degrees Fahrenheit, or 399 degrees Celsius. It is most often observed in heavy wall sections. Reheat cracking is a type of damage that can occur in high-temperature materials, particularly in pressure vessels, heat exchangers, and piping systems that operate in the power generation and petrochemical industries. This phenomenon is predominantly associated with the thermal fatigue of components subjected to cyclic heating and cooling during service. Description of reheat cracking damage as per the following. Mechanism: reheat cracking typically arises when materials, particularly high-temperature alloys or steels, undergo repeated thermal cycling. The expansion and contraction of the material during these cycles can lead to stress concentrations at grain boundaries or through the material. Over time, these stresses can initiate cracks, particularly if the material is also experiencing high levels of thermal stress due to rapid heating or cooling. Number 2 is material factors. Most susceptible are materials that have been subjected to high temperatures and prolonged service life, as they may have undergone microstructural changes, such as the coarsening of grains or precipitation of secondary phases. Materials commonly affected include low-alloy steel, austenitic stainless steels, and superalloys. Number 3 is service conditions. The damage is more prevalent in components operating at high temperatures, typically above 540 degrees Celsius or 1000 degrees Fahrenheit, and under conditions involving thermal cycling or non-uniform temperature distributions. Examples include steam pipes, turbine rotor blades, and furnace components in industrial applications. Number 4 is visual features. Cracking can often be observed as fine, elongated cracks along the grain boundaries. These cracks may propagate through the thickness of the material and can coalesce to form larger fissures, which can significantly compromise the mechanical integrity of the component. Number 5 is consequences. The presence of reheat cracking can lead to catastrophic failures if not detected and addressed, resulting in unscheduled downtime, loss of product, and potential safety hazards. It is, therefore, critical to monitor and inspect for signs of this type of damage using non-destructive testing techniques such as ultrasonic inspection or eddy current testing. Number 6 is prevention and mitigation. To mitigate the risk of reheat cracking, it is essential to select appropriate materials based on their thermal fatigue resistance, maintain effective temperature controls during operation, and implement regular inspection and maintenance protocols. Material treatments, such as precipitation hardening, can also improve resistance to this type of damage. In summary, reheat cracking damage is a critical concern in high-temperature applications, necessitating diligent monitoring, preventive measures, and a thorough understanding of material behavior under thermal cycling conditions. Reheat cracking damage mechanisms affected materials based on API 571, low-alloy steels, especially the CRMO steels with vanadium added, as well as 300 series SS and nickel-base alloys such as alloy 800H. Reheat cracking is a phenomenon that commonly affects high-temperature components in power plants, particularly in areas where materials are subjected to prolonged exposure to high temperatures and cyclic loading conditions, such as in boilers, superheaters, and steam pipes. The primary materials affected by reheat cracking are: Number 1 is carbon steels. These are often used in various components but can be susceptible to reheat cracking, especially in high-temperature regions. Number 2 is low-alloy steels. This category includes materials such as ASTM A335, P1, P5, P9, P11, P22, and P91, which are specifically designed for high-temperature service. Low-alloy steels are often used in pressure vessels and piping. Number 3 is high-alloy steels. Some of these materials, such as AISI 304 and AISI 316 stainless steels, can also experience reheat cracking under certain conditions, particularly when they are subjected to thermal cycling. Number 4 is nickel-based alloys. These alloys are used in very high-temperature applications and can also be prone to cracking if they are not properly designed or maintained. Number 5 is ferritic and austenitic steels. These microstructural categories of steels can exhibit reheat cracking depending on their composition and the stresses to which they are subjected. Reheat cracking typically initiates at the heat-affected zones, or HAZ, of welded joints or in areas where stress concentrations occur, influenced by factors such as temperature gradients, mechanical loads, and material composition. Preventive measures to combat reheat cracking include proper material selection, stringent welding practices, and regular inspection and maintenance of affected components. Reheat cracking critical factors based on API 571. Important parameters include the type of material, chemical composition, impurity elements, grain size, residual stresses from fabrication, cold working, welding, section thickness, which controls restraint and stress state, notches and stress concentrators, weld metal and base metal strength, welding and heat treating conditions. From the various theories of reheat cracking for both 300 series SS and low alloy steels, cracking features are as follows. Number A, reheat cracking requires the presence of high stresses and is therefore more likely to occur in thicker sections and higher strength materials. Number B, reheat cracking occurs at elevated temperatures when creep ductility is insufficient to accommodate the strains required for the relief of applied or residual stresses. Number C, in the first half of 2008, numerous cases of reheat cracking occurred during 2¼ CR/1 MOV reactor fabrication. The cracks were in weld metal only, transverse to the welding direction, and in only saw welds. It was traced to a contaminant in the welding flux. Number D, reheat cracking can either occur during PWHT or in service at high temperature. In both cases, cracks are intergranular and show little or no evidence of deformation. Number E, fine intragranular precipitate particles make the grain stronger than the grain boundaries and force the creep deformation to occur at the grain boundaries. Number F, stress relief and stabilization heat treatment of 300 series SS for maximizing chloride SCC and PTASCC resistance can cause reheat cracking problems, particularly in thicker sections. Reheat cracking, often referred to as Type 4 cracking, is a significant material degradation phenomenon that occurs in high-temperature components, particularly in power plants and industrial boilers. This type of damage generally occurs during the service life of components made from weldable alloys, especially in austenitic stainless steels and some nickel-based alloys. The critical factors contributing to reheat cracking damage include: Number 1 is material composition. The chemical composition of the material, including the content of chromium, nickel, molybdenum, and carbon, can significantly affect susceptibility to reheat cracking. Higher carbon levels can lead to increased precipitation of carbides at grain boundaries, which enhances cracking. Number 2 is heat treatment history. Improper heat treatment can lead to the formation of sensitized microstructures. Solutions that do not include sufficient solution annealing or those that allow for extended exposure to elevated temperatures can promote the formation of detrimental carbides. Number 3 is welding parameters. The welding process itself can introduce residual stresses, altered microstructures, and thermal cycles that predispose materials to cracking. Parameters such as heat input, interpass temperature, and filler material selection can all influence the cracking tendency. Number 4 is service conditions. Operating temperatures and cycle conditions, thermal cycling, prolonged exposure to temperature, are critical. Reheat cracking is often observed in components subjected to long-term high-temperature service. Number 5 is stress levels. Residual stresses from welding and service stresses can contribute to cracking. The combination of tensile stress and elevated temperature increases the likelihood of cracking. Number 6 is microstructure. The presence of specific microstructural features, such as grain size, the distribution of carbides, and phase changes, plays a crucial role in crack initiation and propagation. Number 7 is hydrogen embrittlement. Hydrogen can migrate into the material during fabrication processes, like welding, and operating conditions, leading to enhanced cracking susceptibility when combined with tensile stresses. Number 8 is heat-affected zone, or HAZ. The conditions in the heat-affected zone during welding or thermal cycles can produce a susceptible microstructure that may be different from that of the base metal, making it a critical area for cracking. Number 9 is environmental factors. While primarily related to temperature and mechanical factors, the presence of aggressive environments, e.g., oxidizing environments, may exacerbate crack propagation. Number 10 is component design. Design aspects such as joint design, thickness, and geometry can influence stress distribution and heat flow, affecting susceptibility to cracking. Understanding these critical factors allows engineers and materials scientists to develop strategies to mitigate reheat cracking, including improved material selection, optimized welding procedures, and careful control of service conditions. Reheat cracking affected units or equipment based on API 571, Number A. Reheat cracking is most likely to occur in heavy wall vessels in areas of high restraint, including nozzle welds and heavy wall piping. Number B. HSLA steels are very susceptible to reheat cracking. Reheat cracking damage is primarily associated with high-temperature, high-pressure components in power plants, particularly in fossil fuel and some nuclear power generation facilities. The affected units or equipment typically include: Number 1. Steam generators, components that produce steam from water, particularly those exposed to high temperatures and pressures. Number 2. Superheaters. These devices heat steam above its saturation temperature, and they are crucial in maintaining efficient turbine operation. They are particularly susceptible to reheat cracking due to the extreme temperatures involved. Number 3. Reheaters. Similar to superheaters, reheaters are specifically designed to reheat steam that has passed through the turbine and is returning for further energy extraction. Number 4. Turbines. High-pressure and intermediate-pressure turbine components are at risk, especially those that handle reheated steam. Number 5. Pipes and piping systems. Main steam piping, particularly in the superheat and reheat sections, can be affected by cracking due to temperature gradients and stress. Number 6. Boiler drums and headers. These components are subjected to significant thermal gradients and stresses, making them prone to reheat cracking. Number 7. High-efficiency power cycle components. Any components operating in a combined cycle or ultra-supercritical cycle, where more advanced thermal efficiencies are achieved at higher pressures and temperatures. Number 8. Auxiliary equipment. Pumps, valves, and supports related to high-temperature steam systems can also be affected indirectly by the thermal and mechanical conditions created by reheat cracking in the main components. Reheat cracking is often a concern in materials such as ferritic and austenitic steels, which are used in the construction of the above equipment. Preventive measures, such as material selection, stress relief heat treatments, and regular inspections, are essential to mitigate the risk of reheat cracking in these systems. Appearance or morphology of reheat cracking damage based on API 571, Number A. Reheat cracking is intergranular and can be surface breaking or embedded depending on the state of stress and geometry. It is most frequently observed in coarse-grained sections of a weld heat-affected zone. Number B. In many cases, cracks are confined to the heat-affected zone, initiate at some type of stress concentration, and may act as an initiation site for fatigue. Figure 4, 60-4-63. See Figure 4, 60, samples removed from a cracked 12-inch NPS 321 SS elbow in hot recycle H2 line that operated at 985 degrees Fahrenheit in hydrocracker. See Figure 461, crack at weld from SS 321 elbow shown in the Figure 460. See Figure 462, cross-section through the weldment showing the crack in Figure 461. See Figure 463, photomicrographs of the weldment area. Reheat cracking, also known as hydrogen-assisted cracking or high-temperature hydrogen attack, primarily occurs in high-temperature components of fossil fuel and nuclear power plants, such as turbine rotors, boiler tubes, and pipes. This type of damage typically occurs in heat-affected zones, HAZ, during the manufacturing or welding process, and it may manifest after exposure to high temperatures during service. Appearance or morphology of reheat cracking damage. Appearance or morphology of reheat cracking damage based on crack characteristics includes orientation of crack characteristics. The cracks often have a direction consistent with the stresses present in the material, commonly running perpendicular to the applied stress. Shape of crack characteristics. The cracks can appear as straight or slightly curved but are generally narrow and can propagate over significant distances. Crack characteristics in length may vary in length, often being several millimeters long, but in severe cases, they can extend over larger areas. Number 2 of appearance or morphology of reheat cracking damage is surface features, includes. Number A of surface features is roughness. The surfaces of the cracks may appear rough and can show feathering or sharp edges due to the catastrophic failure mechanism. Number B of surface features is intergranular cracking. The cracks typically follow the grain boundaries of the materials, indicating an intergranular fracture mode. This phenomenon occurs due to the segregation of alloying elements or impurities at the grain boundaries. Number 3 of appearance or morphology of reheat cracking damage is microstructural changes, includes. Number A of microstructural changes is decarburization. The region around the crack may show signs of decarburization or oxidation, leading to a change in the microstructure that contributes to crack propagation. Number B of microstructural changes is phase transformation. There may be phase transformation areas adjacent to the crack, which weakens the material and facilitates crack growth. Number 4 of appearance or morphology of reheat cracking damage is coloration and oxidation, includes. Number A of coloration and oxidation is surface discoloration may be evident, appearing as a result of oxidation. This can include the formation of oxides that are different in color compared to the unaffected base material. Number B of coloration and oxidation is heat tinting. The presence of heat tinting or oxidation scales can be common in areas exposed to high temperatures, often leading to changes in visual appearance. Number 5 of appearance or morphology of reheat cracking damage is location, includes. Number A of location is heat-affected zones. Reheat cracks are typically located in the HAZ of welded joints or near areas of stress concentration, such as corners, notches, or other geometric discontinuities. Reheat cracking can severely compromise the integrity of components in high-temperature environments, making ongoing inspection and material assessment crucial for preventive maintenance. Reheat cracking damage prevention and mitigation based on API 571. Number A, joint configurations in heavy wall sections should be designed to minimize restraint during welding and PWHT. Adequate preheat must also be applied. Number B, the grain size has an important influence on the high-temperature ductility and on the reheat cracking susceptibility. A large grain size results in less ductile heat-affected zones, making the material more susceptible to reheat cracking. Number C, metallurgical notches arising from the welding operation are frequently the cause of heat-affected zone cracking, at the boundary between the weld and the heat-affected zone. Number D, in design and fabrication, it is advisable to avoid sharp changes in cross-section, such as short radius fillets or undercuts that can give rise to stress concentrations. Long seam welds are particularly susceptible to mismatch caused by fit-up problems. Number E, for 2 1/4 cr. 1 MOV saw weld materials, pre-qualification screening tests for reheat cracking such as high-temperature, 650 OC, Glebel tensile tests should be considered. Number F, for alloy 800H, the risk of in-service cracking can be reduced by using base metal and matching weld metal with AL-T. Number G, for alloy 800H which will operate 540 OC, the material may need to be purchased with a thermal stabilization heat treatment, and with PWHT of welds and cold-worked sections. Welds should be made with matching alloy 800H filler material and should be stress-relieved. Refer to ASME Section 8, DIV1 code in UNF 56, E, for additional information. Number H, For thick-wall SS piping, PWHT should be avoided whenever possible. Reheat cracking, also known as high-temperature hydrogen attack, is a type of damage that can occur in high-temperature components of power plants, particularly those that operate at elevated temperatures and pressures, such as boilers, heat exchangers, and gas turbines. This cracking generally occurs in the heat-affected zones, HAZ, of welds or base metals in equipment made from certain grades of steel, especially in a hydrogen-rich environment. To prevent or mitigate reheat cracking, several strategies can be employed. Strategy number 1 to prevent or mitigate reheat cracking is material selection, includes. Number A of material selection is use of resistant alloys. Choose materials that are less susceptible to reheat cracking. For instance, utilizing higher alloyed steels or nickel-based superalloys can enhance resistance. Number B of material selection is controlled chemistry. Ensure alloying elements such as chromium and molybdenum are within specified limits, which can help improve resistance to cracking. Strategy number 2 to prevent or mitigate reheat cracking is welding techniques, includes. Number A of welding techniques is preheating. Preheating the base material before welding can help reduce thermal gradients and residual stresses, lessening the risk of cracking. Number B of welding techniques is interpass temperature control. Monitoring and controlling the interpass temperature during multipass welding can help manage heat distribution and minimize stress concentrations. Number C of welding techniques is welding procedures. Use established welding procedures that are known to minimize the risk of reheat cracking, including proper filler material selection and welding techniques. Strategy number 3 to prevent or mitigate reheat cracking is post-weld heat treatment, or PWHT, includes. Number A of post-weld heat treatment, or PWHT, is stress relieving. Implementing a post-weld heat treatment can relieve residual stresses that may lead to cracking. Number B of post-weld heat treatment, or PWHT, is normalizing or annealing. These processes can help refine microstructures and reduce hardness in affected areas, enhancing resistance to cracking. Strategy number 4 to prevent or mitigate reheat cracking is operational practices, includes. Number A of operational practices is monitor operating conditions. Avoid operating at high temperatures and pressures for prolonged periods, particularly during startup and shutdown cycles. Number C, embedded cracks can only be found through UT examination. Number D, inspection for reheat cracking in 2¼ CR 1 MOV reactors during fabrication is typically done with TOFD or manual shear wave UT, with the demonstration block having defects as small as 3 mm side drilled holes. Reheat cracking damage is a form of degradation that can occur in austenitic stainless steels, particularly in components of power plants that operate at elevated temperatures. Detecting reheat cracking is crucial for ensuring the safety and performance of these systems. Several inspection and monitoring methods are commonly employed to detect such damage. Number 1 is visual inspection, surface examination. A thorough visual inspection can reveal surface breaking cracks, discoloration, or deformation that might indicate reheat cracking. Number 2 is magnetic particle testing, MPT surface and near-surface detection. This method is useful for detecting surface and near-surface discontinuities in ferromagnetic materials. It involves the application of a magnetic field and the use of fine magnetic particles that gather at defects. Number 3 is liquid penetrant testing, LPT surface crack detection. Liquid penetrant testing is designed to expose surface breaking defects by applying a colored or fluorescent dye that penetrates cracks and can be visually inspected. Number 4 is ultrasonic testing, UT thickness and flaw detection. Ultrasonic testing can be used to estimate material thickness and identify internal flaws. Advanced techniques like phased array ultrasonic testing, PUT, can enhance detection capabilities. Number 5 is liquid penetrant testing, LPT surface crack detection. Liquid penetrant testing is designed to expose surface breaking defects by applying a colored or fluorescent dye that penetrates cracks and can be visually inspected. Number 6 is ultrasonic testing, UT thickness and flaw detection. Ultrasonic testing can be used to estimate material thickness and identify internal flaws. Advanced techniques like phased array ultrasonic testing, PUT, can enhance detection capabilities. Number 7 is eddy current testing, identifying material changes. Eddy current testing is effective for detecting surface cracks in nonferromagnetic materials and can also assess changes in material properties due to reheat cracking. Number 8 is radiographic testing, RT internal flaw detection. Radiographic testing utilizes X-rays or gamma rays to identify internal cracks or voids, although it can be less effective for small cracks compared to other techniques. Number 9 is acoustic emission, AE, monitoring. Real-time monitoring. Acoustic emission techniques involve listening for high-frequency sound waves emitted by crack formation and growth, providing insight into structural integrity over time. Number 10 is thermography, temperature profiling. Infrared thermography can be used to identify areas of abnormal temperature distribution that might indicate underlying cracks or defects. Number 11 is strain gauges and monitoring, stress analysis. Installing strain gauges on critical components allows for direct measurement of stress and deformation over time, which can help predict crack initiation and growth. Number 12 is fracture mechanics assessments, evaluating crack severity. After initial detection, detailed analyses using fracture mechanics principles can be performed to assess the severity and potential propagation of detected cracks. Number 13 is chemical analysis, material composition evaluation. Chemical analysis of the metal may help identify susceptible areas by checking for factors such as carbides that could contribute to reheat cracking. Conclusion: effective detection of reheat cracking typically involves a combination of methods to ensure reliability and comprehensiveness, especially in critical applications like power generation. Regular inspection and monitoring are essential for maintaining the integrity of components susceptible to this type of damage. Thank you.